for any flows, you can decompose the general 3x3 matrix, 9 independent components, plus a linear translation. So basically the first two terms in the Taylor series expansion of the flow field. You have a flow field velocity as a function of x and y, right? You take a Taylor series expansion. The first term is at this point is just the velocity at this point. The second point, you consider infinitesimal movement in x, y, z direction, how the velocity changes. That's the contribution from the velocity gradient tensor. So what we are saying is that the first two terms in the Taylor series can be expanded into a linear translation, anti-symmetric gradient, which is rotation, a divergence, which represents the rate of expansion, and if you follow the conservation of mass equation, this term is going to be exactly the this term times the local gradient, local density is going to be the Lagrangian rate of change on the density itself, right? So if you have a locally expanding flow, the density is going to change proportionally lower. If you have a negative divergence, the density is going to increase proportionally as time goes forward. All right, and so a general hypothesis is that this term does not contribute to the viscous stress tensor. Okay, if you consider the entire stress, like on the entire stress, including the viscous stress and pressure, the pressure actually corresponds to an isotropic stress, right? And because the pressure force is because the pressure stress is in most flows is a lot larger than any effect of viscosity, it is generally assumed that the viscosity contributes nothing into that isotropic component. And experimentally, it's very hard to test that, right? So although it's not just because the pressure is usually that much larger, okay, and but like computationally, so it's pretty safe to assume that the isotropic diagonal component is mostly due to pressure and not due to viscous forces. Okay, now what's left is these two. All right, these two are off-diagonal components of a symmetric tensor and also diagonal components of a tensor whose trace, or the sum of all the diagonals, is equal to 0. Now it turns out that under coordinate transformations, these can actually go either way. You can make a general symmetric and trace-free tensor. Trace is basically the sum of the diagonal components. Trace-free means the sum of the diagonal components equal to 0. You can make a symmetric trace-free tensor to be diagonal, right, in or off diagonal, like in whatever way you want. So through a solid body rotation. And mathematically, if you want to make this diagonal, if you want to make this tensor diagonal, what do? If you're in MATLAB, we're going to be using MATLAB a lot in this class. If you are in MATLAB, I give you a tensor 3x3 matrix. I want to see what coordinate transformation or rotation should I do to make this tensor to be diagonal. What should I do? Find the eigenvectors, right? So that's a very good suggestion, because if we have a symmetric tensor, the eigenvectors are automatically going to be orthogonal to each other, and that corresponds to a rotation, right? That corresponds to I shouldn't say that corresponds always to a rotation. That corresponds to a rotation plus a reflection, right? And you can always change the signs of these diagonal entries so that you don't have any reflection in your in your eigenvalues, eigenvectors, I should say. All right. I'm just going to give you an example. If I have the tensor, let me see. So if I have the tensor we defined the last lecture, so 0, 1, 1, 0, right? So 0, 1, 1, 0 corresponds to the velocity strength tensor, corresponds to the symmetric part of the velocity strength tensor in a parallel shear flow. If you have two walls, the bottom wall is not moving, the top wall is moving, and the velocity profile is just a linear varying between these two walls, this is the symmetric part of the velocity strength tensor, right? So if you just do eigenvalue analysis of S, I'm going to get, okay, so the eigenvalues are -1 and 1. That means after symmetrization, the diagonal entries are going to be -1 and 1. Now, what is the matrix you use to do symmetrization? So I'm going to say lambda L and V equal to that. So I'm going to go, well, that's actually the opposite, should be V and L. So V is the rotation I need to apply. So it turns out to be, well, it turns out to be that matrix, but I need to actually reflect the first column or the first row to make it a rotation matrix. Otherwise, this one actually contains a reflection, right? So if I make the first eigenvector to be negative of what is shown on the screen, right? Which is also an eigenvector, right? So eigenvector doesn't change under a scaling, under constant scaling. So I do a constant scaling of -1 to this one, I get, so this is the minus square root of 2 divided by 2, right? Or cosine or sine of 45 degrees. So if I make this positive and this negative, I get two coordinates, both pointing 45 degrees. All right, so that means for this tensor, for this particular tensor, that's exactly what I'm drawing in this one, right? This is the tensor I have in this particular S.
Could you explain once again why you multiply minus 1 to the first column?
Why did I multiply -1 on the first column? That is because, let me see. So the first column is minus plus, so let me draw it. The first column is minus plus, so that's this direction. The second column is plus plus, so it's in this direction, right? So if I have my x, y, then my x prime and y prime are going to be like this and this. So you can see I have no way I can do rotation to x and y to make it x prime and y prime, right? So how can I rotate x and y to this x prime, y prime? I can't, right? I have to first flip it over and then rotate. That's why I need to multiply, basically I need to make this x prime to be pointing in the other direction before I can have a rotation, so that xy matches x prime, y prime, right? So this doesn't affect the eigenvectors though. It doesn't affect the eigenvalues though, right? Yeah, any other questions? So basically we can see that if you do this coordinate transformation, so this is the x prime I want to use, right? So if you make this x prime and y prime, these are the two directions, right? That if you look at these two directions, I'm actually elongating along particular axis and shrinking along other axes. Under the 45-degree angle, this purely off-diagonal velocity gradient tensor is actually purely diagonal, right? So there is no physical difference between off-diagonal and diagonal. strain tensors. Make sense? All right. Okay, so the next topic we are going to talk about is, now we have all the governing equations with the viscous stress tensor, right? So the viscous stress tensor is basically, I need to write it as tau is going to be proportional. It's going to be proportional to the symmetric trace-free part of the velocity strain tensor. So basically, I need to say this is proportional to gradient of u plus gradient of u transpose, but I need to subtract from the diagonal part, right? The sum of the diagonal parts. So if you look at this, let me actually put a divide by 2 here, so that the diagonal entries are replicated only once, right? So each diagonal entry here is added once. So what I need to do is, in order to add a something times identity to make this trace free, okay, what I need to do is I need to have a 3 here, because there are 3 diagonal entries, and sorry, 3 should be down there, right? 1/3 times identity times the divergence of u, right? And usually we write we define the viscosity to be proportional. I mean, the convention is define the viscosity in a way that it is proportional to just the grad of u. So the convention is have a 2 mu here on the whole thing to cancel out the factor of 2 here. So that's the usual form of viscous stress tensor in a Newtonian fluid. This is basically a definition of Newtonian fluid. Yeah, that's right. So for fluid satisfying this relationship, we call it a Newtonian fluid. Basically, the velocity strain and the viscous stress following a linear relationship. For non-Newtonian fluids, the relationship can be nonlinear, right? So if you have a higher magnitude of strain rate or lower magnitude of strain rate, the viscous stress can be higher or lower than for a Newtonian fluid.